All right, so just like we did for Chem 141, at least if it came to any of my reviews, I'm just going to go through the set of practice problems that we have posted up on D2L, and if there's one that you want to see, just say yes. If you don't want to see it, don't say anything, and if nobody else says yes, we'll just move on to the next problem. So we'll just go like that. All right, so number one. Yes? Okay, so number one says stainless steel is an example of what type of solution? Well, if you think of stainless steel, so this is like what your silverware might be made out of, your everyday silverware, and of course, you know that's a solid there. Is it made up of a liquid in a liquid? That would be hard to eat with. Is it made of a gas in a solid? Once again, that would, those type of mixtures do exist, but probably not for something like stainless steel. Solid liquid. Well, once again, if you had a liquid component in your silverware, that would be kind of weird. So that would be a solid-solid mixture. So what you have is you have one solid that's dissolved in another solid. Now, when it's made, being made, you have a liquid solution, and then it cools and it solidifies, and it becomes a solid solution. So you have a solid solute in a solid solvent, is what that means. All right. Number two. Yep, sorry.
What would an example of a solid liquid be? Do you have an example?
Well, that'd be like dissolving salt in water. Solid liquid, yeah. All right, let's see here. How about three? Yeah, I knew that was coming. Don't be shy about saying, yes, I want to see one. If you want to see it, say it. Otherwise, I'm not going to do it. So, okay, so number three says aqueous solutions of 30% hydrogen peroxide H2O2 are used to oxidize metals or organic molecules in chemical reactions. Calculate the molality of this solution. So we're told that it is 30% by weight. And so what we really need to figure out is what exactly does that 30% mean? Well, it means that 30 of the 100 grams of solution are made up of hydrogen peroxide. So what we've really got in a 30% solution, if we imagine that we have a 100 gram solution, we're going to have 30 grams of H2O2 and 70 grams of water, because it's an aqueous solution. So that's our 100 grams of solution, 30 of which are made up of the hydrogen peroxide, H2O2. Okay, so we want to know the molality of this solution. So what we need to calculate is the number of moles of H2O2 over the number of kilograms of water. Okay, the kilograms of water is easy because we have the grams. The calculating moles from grams on the hydrogen peroxide isn't hard either, but, it takes a little bit more work. And so for that one, we need to calculate our moles of H2O2. And so that's going to be equal to 30 grams times 1 mole per. So we just need the molar mass of H2O2, and that's 34 grams. And so we end up with 0.882 moles of the hydrogen peroxide. And so to calculate the molality, so that's going to be our moles, so 0.882 moles over the number of kilograms of our solvent, so that's going to be 70 grams, so that's 0.070 kilograms. And so when we work that one out, we get 12.6 molal solution there, so that's B. Yeah, if you try to calculate that with 100 grams of water, because it's not 30%, it's 30% by mass, that's 30 out of the total, not 30 that plus 100 of waters. That's always a hard thing to remember. Questions on that one at all? All right, number 4. Yes, so We want to know what are the major solute-solvent interactions created when KBr dissolves in water. So, the first thing we need to recognize is what kind of compound is KBr. Well, it's a metal and a non-metal. And so when you put that into water, it's going to break up into potassium ions and bromide ions. So you've got ions there. So now you know you're going to have an ion present. And then with water, of course, the thing that makes water such a good solvent is the fact that it is polar and it has a dipole. We've got that delta minus on the oxygens, the little delta pluses on those hydrogens, and those delta minuses and delta pluses on the hydrogen or on the water allow it to interact electrostatically with the pluses and the minus of the ions. And so water's dipole interacts with the ions, so we call it an ion dipole interaction. So the answer there would be B, ion dipole. Okay, it definitely also has dispersion interactions. Every molecule, every atom has London dispersion because every atom molecule has electrons. But it says what is the major solvent interactions there. All right, questions on that one? All right, number 5. Is that yes? Okay. So it says, for which case would the delta H solution be expected to be negative? So remember, our delta H of solution has 3 components to it. Okay, so we've got our solute interactions, and that always raises the energy up. So here's our starting point. Okay, so solute, and then we've got to break solvent interactions. We've got to make room in the solvent for those particles to go into, those solute particles to go into. So that is also a positive interaction because you're breaking that attractive interaction there. And then you've got this interaction here. Now, if you want to have your delta H of solution be negative, you have to finish with lower energy than you started. Okay, so if we think about these energies here and this energy here, okay, what has to be true? Okay, well, let's see. So if we had A, if solute-solvent interactions are the same as solvent-solvent and solute-solute interactions, well, that would bring the energy to the exact same space, and you would have the delta H solution of 0 if they were exactly the same. So you have energy that went in and the energy that came out exactly the same. So the correct answer here is B. Solute-solvent interactions are much greater than solvent-solvent and solute-solute interactions. And so that means that more energy was released than had to be absorbed. And so that's why the delta H is negative. It means you have a net release of energy when that substance dissolved. Yeah?
So solute solvent are negative, and then solvent are positive?
That's correct. Because you have to add energy to separate the solute particles away from each other. And you also have to add energy to move the solvent molecules away from each other. But then when you form those attractive interactions between the solute and the solvent, it's going to release energy. Yeah, that takes us way back. That was like first or second day of class. All right, number 6. You guys good calculating molality? Good. Number 7. Yes, okay, so we're looking for mole fraction in a solution made by dissolving 27.8 grams of iodine, I2, in 245 grams of hexane, which has a formula of C6H14. So we've got masses of our solute and our solvent, but if we're going to do mole fraction, we need to know our numbers of moles. Okay, so let's go ahead and do that. So let's write what our mole fraction is going to be. So we want the mole fraction of I2. Oh, sorry. So our mole fraction of I2 is going to be our number of moles of I2 over the number of moles of I2 plus the number of moles of our hexane. Okay, so we need to calculate the number of moles of both of those. One thing people frequently forget to do is to include the moles of our solute in the total number of moles. Okay, which is they still count there. Okay, so we've got 27.8 grams of I2 times 1 mole. You can't forget that it's I2. And so that's 253.8 grams per mole. And so that gives us 0.1095 moles. And for our hexane, we've got 245 grams. I'm just going to put hex times 1 mole. And that has a molar mass of 86 grams per mole. And so that comes out to 2.848 moles. And so my mole fraction of I2 is going to be equal to my number of moles of I2, so 0.1095 moles over 0.1095 moles plus 2.848 moles. And when we calculate that out, we get 0.0370. And the mole fraction there is unitless. It has no units. It's just a fraction. The moles cancel out. Questions on that one at all? Okay. That was 7. How about number 8? Yes. Okay, so we want to know what volume. This takes us back a little bit to Chem 141. We had done some of these last semester, but also in the solutions chapter here. What volume of 0.716 molar KBr solution is needed to provide 10.5 grams of potassium bromide? So we need to work kind of backwards. We've got number of grams of KBr. From the number of grams, we can figure out how many moles that's going to be. And then because we know the molarity of the solution, we can figure out how many liters of that solution are going to give us that many moles. So we'll kind of work it backwards there. So for number 8, we know we've got 10.5 grams KBr times, so we're going to convert that into moles. So that's 119 grams per mole. And so that gives us 8.82 times 10 to the minus 2 moles. Okay, so that's how many moles we need. We know that molarity is equal to moles over volume. Okay, where volume's in liters there. And we're looking for a volume, so we can rearrange this to solve for volume, and we get volume is equal to moles over molarity. Okay, so we can solve that. So we get 8.82 times 10 to the minus 2 moles all over our molarity, which is 0.716. And that's moles per liter. And so our moles are going to cancel. And when we calculate this out, we get 0.123 liters, and we convert that to milliliters, and we get 123 milliliters. Any questions on that one at all? All right, let me flip my page here. Okay, number 9. Yes. So we want to know what is the mass percent of a caffeine solution made by dissolving 4.35 grams of caffeine in 75 grams of benzene. Okay, so this is kind of similar to the mole fraction problem. When we're doing mass percent, you've got to remember that's going to be the mass of whatever we're looking for, in this case the caffeine, over the total mass not just the mass of the solvent. And then, of course, for mass percent, we need to multiply by 100. So for our mass percent here, we've got 4.35 grams of our caffeine over 4.35 grams plus the 75 grams of the benzene there. And then we need to multiply that by 100 to give us a percent. And when we work that out, we get 5.5%. Okay, if you forget to include that 4.35 grams on the bottom, you're going to get a different answer, obviously. You probably get A. Okay, any questions on that? And then don't forget to multiply by the 100. It looked like they accounted for that one as well. All right, number 10. Oh, yeah, okay. So 10's pretty straightforward. We just have to remember how solubility goes with our different components. So solubility of gases, okay, in water, what do they do with temperature? As temperature goes up, what happens to the solubility of the gas? It goes down. Okay, so as temperature goes up, it can hold less and less gas. Again, remember, the only way I can remember that, well, two ways to remember that, is that a warm soda goes flat really fast because it can't hold on to that dissolved carbon dioxide, or it's also the reason that they call off the fishing on hot days because the rivers warm up and they can't hold as much oxygen and the fish are suffocating. Okay, so as temperature goes up, less gases are held. And for the solubility of solids in water, what does the solubility there generally do? Generally goes up. And again, think of iced tea versus hot tea. Iced tea, you get the sugar boogers that take a day to dissolve. Hot tea, it takes a few seconds. Okay? Again, that's a general rule. It's not an everything rule. There are some things that actually decrease in solubility with raising temperature, but they're a lot fewer things than what increases with increasing temperature. All right. Number 11. Yes? So number 11, you got to read really carefully. So the correct answer there is D. Let's just talk about why that's the correct answer. So reduced boiling points of pure liquids at increased altitude. So that's not a colligative property because, one, it's colligative properties apply only to solutions. And so here we're talking about pure liquids, which are not solutions. But also all we're doing here is just reducing the pressure above that liquid, and it's causing it to boil sooner. So colligative properties are caused by the addition of a solute to a solvent. And so you're changing it into a solution and changing the properties of what the solvent had in it when it was pure. So that's the colligative property. So that's why D is the correct answer of not being a colligative property, because that involves a pure solvent. Okay? That one's a tricky read. I knew that was going to be a bit of a tricky read. All right, number 12. Yeah, probably didn't even need to ask that one. I got that one a lot today in my office. What is the expected freezing point of a 0.50 molal solution of sodium sulfate, Na2SO4, in water? And we have the Kf for water. Okay, so we got 12. Okay, so one of the most common questions I've been asked in the last few weeks is, when do I use I and when don't I use I? Okay, the answer is you can always use I in these colligative properties. It's just a matter of knowing what I is. Okay, so we can write here, we can write delta TF, because we're looking for a freezing point, is equal to I times KF times M. Okay, the only time I is really important is when you have an ionic substance, because ionic substances dissociate in solution and form multiple particles. And you always know you have an ionic substance when you have a metal and a non-metal. Okay, or if you have, you can even have two different polyatomic ions, like ammonium nitrate or ammonium sulfate. Okay, but you've got to recognize when you're going to have ions. If you have something like sugar that just has carbons, hydrogens, oxygens, those are molecular compounds. They don't dissociate, so they have an I of 1. So you can still use I for those molecular compounds, it's just that they have a value of 1. So it doesn't really factor in. But when you have an ionic substance, such as this one, which is sodium sulfate, Na2SO4, when you put that into water, it's going to break apart into 2 sodium ions and a sulfate ion. Okay, so I've actually created 3 particles there. So for every 1 mole of sodium sulfate I put into solution, I'm going to get 3 moles of particles. And so I'm going to have an I value here of 3. Okay, so basically I is the number of particles that it breaks up into when it dissociates. Okay, so what we're going to do here is just going to do our new delta TF is equal to I, so we're going to have 3 times our KF, 1.86, and that's degrees C per molal, and our M we were given at 0.50 molal, so our molalities cancel, and we get a delta TF that's equal to 2.79. And again, this is a depression, so we're always going to drop our freezing point. And since water is normally at 0, this becomes negative 2.79 degrees Celsius. And we only get 2 sig figs there, so it becomes 2.8. Negative 2.8. Okay, I do give you the table of polyatomic ions that we got last semester, so if you need to see, it's like, oh, NO3, is that a polyatomic ion? You should recognize that. You should recognize most of them. It's been a little while. So just look at that table and say, oh, yeah, it's polyatomic ion. Remember, those don't break apart into all of their various atoms. Okay, they stay lumped together. And NO3 is an ion, and it stays as that one big ion. Okay? All right. Questions on that one at all? Yeah. Oh, yeah. I always give you a periodic table. Yeah. I couldn't ask you to do molar mass stuff without a periodic table. I can't do molar mass stuff without a periodic table. Unless it's hydrocarbons, then it's easy. All right. Number 13. Yeah, okay. I was waiting for that. It's like 13. I got asked that one a lot today, too. So it says a solution is made by dissolving 13 grams of sucrose. We've got the formula and molar mass in 117 grams of water, producing a solution with a volume of 125 milliliters at 20 degrees Celsius. What is the expected osmotic pressure at 20 degrees Celsius? Okay, so we're looking for osmotic pressure. Remember, osmotic pressure is pi is equal to C RT, where C is our concentration in molarity. R is the gas constant, so we want R at 0.0821 liter atmosphere per Kelvin mole. And then T is our temperature in Kelvin, so we've got to have Kelvin. The other question I got asked a lot this last week is, how do I know which R to use? Okay, because we've seen a couple of different R's. We've got an energy R, and we've got a gas pressure R. Okay, if there's anything involving gases and volumes, then you're going to use this R. Okay, because it includes things like liters and atmospheres. Okay, if you have anything that includes energy, such as joules, then you use the other R because that has units of joules. The two values of R are identical. They just have different units, and that's why they have different values, but they represent the same constant. Okay, they are the same constant, just with different units. So you got to make sure you use the right one. So that's why unit analysis becomes real important. If you're trying to cancel out liters and atmospheres with joules, you got the wrong R value. Use the other one, okay, or vice versa. All right, so we need to calculate the molarity here. We have a mass of sucrose there. We've got to find how many moles that is. So we've got 13 grams of sucrose, and it's got a molar mass of 342 grams per mole. So that becomes 3.80 times 10 to the minus 2 moles. Okay, so that's how many moles I have. And we're looking for a molarity for our concentration, so we use molarity as moles of solute over liters of solution. We know that when we added the sugar, we got 125 milliliters of solution, or 0.125 liters of solution. So our molarity, or I guess I could call it C, is going to be equal to 3.80 times 10 to the minus 2 moles over 0.125 liters. And so you get a concentration here of 0.304 molar. Okay, now I have everything that I need. Oh, our temperature is 20 Celsius, which is going to be 293 Kelvin. You've got to use that Kelvin temperature. And so our osmotic pressure is going to be our concentration, 0.304 moles per liter. I'll go ahead and work out the units here. R, 0.0821 liter atmosphere per Kelvin mole times 293 Kelvin. And you can see my Kelvin cancels, my liters cancel, my moles cancel, and that leaves me only with atmospheres, which is good since I'm looking for a pressure. And we get a value of 7.32 atmospheres, or 7.3 to 2 sig figs. Questions at all? Yeah.
How come you use a little c instead of big F?
Oh, it's just a way of saying concentration. Yeah, it's not important. I could have just as easily used down there. All right. Any other questions on that? Okay. Number 14. Yeah. So it says, which term describes the measure of the increase in the concentration of the product per unit time? So we're looking at really just change. We could have just as easily said the change in the concentration of the product per unit time. Okay, and that's going to be our reaction rate. Okay, we have change in concentration per unit time. So we have like delta concentration of A over delta T. That's how we define concentration, or that's how we define reaction rate. Change in concentration over time. Kinetics is the field that involves all of that. Reaction time, that's just time we get the reaction time. And activation energy, that's just the energy difference between the starting energy of your reactants and the highest energy point in that reaction. So that's what activation is. Okay, so the answer there would be C, reaction rate, or rate of reaction. 15. Oh, okay. I thought we were going to get away with one there. So 15. Molecular hydrogen can be made from methane gas by the reaction below. It gives a reaction there. How is the rate of disappearance of CH4 related to the rate of appearance of H2? So all we're really looking at is just how would we express the different rates of reaction based on all the different reactants and products there. So if we look at 15, did I skip a number? Oh, this was 13, not 14. There we go. So 15, we've got negative delta concentration of CH4 over delta T. So that's the rate of the reaction, okay? Because we see that CH4 is a reactant, so we have a minus sign. It has a coefficient of 1, so we just have 1 over 1 there, which we don't usually write. So that is the rate of reaction based on the CH4. So if we look at the rate of reaction based on H2, well, it's a product, so that's still going to have just a plus there, which some people write, some don't. Oh, the answer wrote it, so that's good. And then I take the inverse of its coefficient, so 1/3, and then the change in its concentration over the change in time. Okay, so what that says is that the hydrogen is going to change 3 times faster than the rate of CH4. So I have to multiply the rate of the hydrogen by 1/3 to bring it back down to the same level. And that would make sense since for every, I don't have it up there, for every 1 mole of CH4 that gets reacted, 3 moles of H2 get formed. Okay, so the rate of appearance of the hydrogen is 3 times faster than the methane. questions on that one at all? I could have also have expressed it for the CO. That would have been the same as for the CH4. It just would have had an opposite sign. Same with the H2O. That actually would have been the same as the CH4, since they both have a 1 coefficient. 16. Yeah, I should just know that one. I get asked that one every year. All right, so 16 says the reaction that occurs in a breathalyzer device used to determine the alcohol level in a person's bloodstream is given below. If the rate of appearance of the chromium sulfate is 1.24 moles per minute at a particular moment, what is the rate of disappearance of the ethanol, C2H6O, at that moment? Okay. Well, if we so we have a rate of appearance of just the chromium sulfate there. Okay, so that's not the rate of the reaction. That's just for that component. So we want to compare the rate of reaction based on the chromium sulfate and equate that to the disappearance of the ethanol. So what we can write is 1/2. We don't really need to include positives and negatives here. And the reason for that is because the wording already specifically states that things are appearing or disappearing. So we've got the concentration of the chromium sulfate over delta T. And the reason we have the 1/2 there is because that chromium sulfate has a 2 coefficient in front of it. Okay? And so its rate of appearance is going to equal, its rate of appearance is going to equal 1/3 the change in concentration of the ethanol. Again, we use that 1/3 because there's a 3 coefficient in front of the ethanol, the C2H6O, in the balanced reaction. Okay, now we are given a value of 1.24 moles per minute. That is what this is right here, without the 1/2. Okay, so I know the change in the concentration of the chromium sulfate with respect to time. Okay, just that. And then I put that in terms of the rate of the reaction by incorporating that 1/2. So I now have 1/2 times 1.24 moles per minute is equal to 1/3 times the change in concentration of our ethanol. Okay, well, this whole thing here is what I'm looking for. Okay, that change in concentration of the ethanol with respect to time. So all I need to do is to multiply both sides by 3. And so that's going to give me 3/2 times 1.24 moles per minute is equal to the change, the concentration of the C2H6O with respect to time. And when you calculate that out, you get 1.86 mole per minute. Any questions on anything I did? That's a hard problem. Okay, the math isn't hard. The math's fairly easy, but seeing what needs to go where is really the hard part. How to set that one up. All right. I'll change that page. Change this page. All right, so you'll notice that 17 is crossed out. It's just a disaster of a problem. I crossed that out a few years ago. It's hard for me to try to delete it out of a PDF, so I just crossed it all out. That one was just, that was a disaster. So we'll just jump to 18. Any questions on 18? Yes. So we've got a diagram there. It says the energy of reaction. Delta E is given by the difference in energy between which two reaction stages in the above reaction coordinate diagram. Okay? And so if we look at that, I'm just going to scribble our diagram here a little bit. Okay, so we've got energy here, and we've got our reaction coordinate here. Okay, so in some books, you'll see delta E. Our book uses delta H. Okay, so that's the same thing. So delta H, if you remember, delta H for a reaction is always where did you finish minus where did you end up. Okay, so we've got points 1, 2, and 3. And so it's going to be, to figure out our delta H or our delta E, we want to know this difference in energy right there. That's our delta E. Okay, so that's going to be the energy at point 3 minus the energy at point 1. How about activation energy? What would activation energy be? 2 minus 1. We had that on the clicker the other day. Good. What's that? Activation energy would be the energy at point 2 minus the energy at point 1. Okay, that distance in energy up to that highest point. All right. Number 19. You good at that one? Okay. Number 20.
Yeah.
Sorry, what is it?
Can we go over 19, please?
You do want to go over 19. Okay. I'm sorry?
Why is it not 8?
Because they can be 0. Yeah. They can actually also be negative. Yeah. So, especially when you're getting into the fast, slow things. If you ever have a reactant that ends up in the denominator, that's technically a negative exponent. So, but they can also be 0. All right, so 20. Somebody said they wanted to see 20. So for a reaction that follows the general rate, R rate equals KAB squared. What will happen to the rate of the reaction if the concentration of A is increased by a factor of 3? So we didn't talk a whole lot about this. This is just kind of, you want to look at this, do a little mental math there. Okay, so the thing you need to think about is that K is a constant. The way the problem is worded, you would assume that the concentration of B remains the same, that you're only changing A. Okay, so when we're calculating the rate, we have a value of K that doesn't change, a value of B that doesn't change. And so if I increase the concentration of A by a factor of 3, what's going to happen to the rate? It's going to go up by a factor of 3 because if B stays the same and K stays the same, then the only thing changing is A, and so it would go up by a factor of 3 because it's just to the 1 power. The harder question, what would happen if I changed B by a factor of 3? The rate would go up by a factor of 9, okay, because the factor of 3 gets squared in there. Okay? So whatever you do to that concentration in the rate law, its effect on the rate takes into account that exponent as well. So if I doubled something that was squared, it would make the rate go up by a factor of 4. If I doubled something that had an exponent of 1, then it would just double the rate. Okay? 21. Really? Okay. You're going to laugh when you see that. So we want the overall reaction order. So remember, for overall reaction order, if we have rate equals K, I'll just say concentration of A raised to some M, concentration of B raised to some N, then the reaction order is equal to M plus N. So we have H2 to the first, NO to the second, so 1 plus 2 is 3, third order. That's all it is. So you just add those exponents. The sum of the exponents, that's the order. You got 1 and 1, then it's 2. You got just 1, then it's 1. Those are nice questions. 22. Yes. Okay, we had a problem similar to that in class, but we didn't take it quite this far. In class, we worked out the rate law, but we didn't find K. So for 22 here, we've got a set of data there. So let's just go ahead and we'll do the HgCl2. In order to find the K, the first thing we've got to do is we've got to find the rate law. And we can't do K without the rate law, so we've got to find that first. So for the HgCl2, we want to pick 2 experiments where the HgCl2 changed and the C2O4 did not change. So which 2 do we want to use? What do you think? 2 and 3. Okay, because the C2O4 is 0.2 in both of those, but the HgCl2 changed. So, which has the faster rate, second or third? Okay, the third does. It's 1 times 10 to the minus 6. You got to be careful because that second one says 5.2, but that's times 10 to the minus 7. So you got to watch for those exponents. Those trip some people up. So our faster rate is 1.0 times 10 to the minus 6. We do rate fast over rate slow. And that's going to be equal to the faster concentration, so 0.2, over the slower concentration, 0.1. That's going to be raised to some x. Okay, and we work out that math. I didn't actually do that one on the calculator. Those are the concentrations of the HgCl2 for experiments 2 and 3. So you get 1.92 is equal to 2 to the x. Well, that's essentially 2 is equal to 2 to the x. Remember I said you can do some pretty liberal rounding with these rate laws because the data is really hard to get exact. And so we get an x value here of 1. So our exponent for the mercury chloride is 1. And then for the oxalate ion here, that C2O4 minus, which 2 experiments are we going to use here? 1 and 2, because our HgCl2 remains the same. So the faster one is going to be experiment 2. So 5.2 times 10 to the minus 7 over 1.3 times 10 to the minus 7. That's going to be equal to 0.20 over 0.10. That's going to be the sum y. So that comes out to be 4 is equal to 2 to the y. So y here is equal to 2. Okay, so now we can write our rate law. We can say that rate equals K, concentration of HgCl2, concentration of C2O4 minus, and that gets squared. Okay, so that's our rate law now. And what we can do now to find the K is to pick any one of those 3 experiments, and it doesn't matter which one. We take the rate, we take the concentrations of the 2 reactants, plug them in, and solve for K. I just picked the first one just because it was there. So I did 1.3 times 10 to the minus 7 is equal to K times 0.1 times 0.1 squared. And when you do that and solve for K, I got 1.3 times 10 to the minus 4. And it's a third order, so that's going to have units of 1 over molarity squared seconds. Questions on any one of that data?
Can you just review the units for the first, second, and zero?
We can't. I don't test you on the units for these, but I'll go ahead and mention it because somebody someday might quiz you on it. The thing to remember is that your rate is always going to have units of molarity per time. And once you know that, then you can adjust the K to end up with those units. They just have to, it's always going to be 1 over something time, and then your molarity is either not going to be there, or it's going to be the first power or the second power to cancel out enough of the molarities to leave 1 from the concentrations. Okay? All right. That was 22. 23. Yes. 23 says, for a particular first order reaction, it takes 48 minutes for the concentration of the reactant to decrease to 25% of its initial value. What is the value for the rate constant in inverse seconds for the reaction? Okay, this problem has a couple of sneaky little twists to it. Okay, one sneaky twist is that they gave you 25% of its original value. Okay, so there's a couple ways you can do this problem. The easy way is to recognize that this is one of those magic numbers I talked to you about. Okay, because if you're doing a half-life, something's decaying, you can go from 100% to 50% down to 25%, and that takes 2 half-lives. Okay, so from 150 and then from 50 to 25. So that took 2 half-lives, and then I know that took 48 minutes. So if 48 minutes is 2 half-lives, then what's 1 half-life? It's 24 minutes. So I know that my T 1/2 is equal to 24 minutes. Okay, now, the other thing, sneaky, that they did, is they gave us our time in minutes, but look at the units of K that they want. It's in inverse seconds. So that means I've got to convert these minutes into seconds. If you don't convert them into seconds and use the minutes here, you're going to get a different K, and lo and behold, that's answer A. And the reason I know that is because I didn't pay attention to my units, and that's when I circled first, and I said, oh, that doesn't look right, and so I had to go back. It's like, I made that silly mistake that I know people make. This is why I don't do this to you on a problem, because I don't think it tests the right thing. So anyway, so let's convert this to seconds, and so our half-life becomes 1440 seconds. Okay, so now we have our half-life in seconds. We know that the half-life is equal to the natural log of 2 over K. I can solve that for K, and I get K is equal to natural log of 2 over my half-life, and so K is equal to natural log of 2 over 1440 seconds. And when you plug that in, you get 4.8 times 10 to the minus 4 inverse seconds. Questions at all on that one? The other way you could have worked this one, it's just like I showed you in class. If you don't recognize one of those magic numbers, you can just do your natural log of AT over A0 concentration is equal to negative KT. Since you know that you're 25% of your original value, you know that the ratio of 8 times T over 8 times 0 is 0.25, because you're a quarter of what you started with. And you know T, but again, you want to change that T into seconds, that 48 minutes into seconds. Okay, so either of those ways will work. They'll give you the same answer. All right, let me change page. Let's see, that was 24, 25. Okay, it's D, bromine. Remember, catalyst is something that shows up first as a reactant, then gets spit out as a product. Opposite from the reaction intermediate. Let's see, 26. Yes? Okay, 26, pretty much a plug and chug, very similar to the problem we just worked. So we're looking for the half-life. We know that the time for a half-life is equal to natural log of 2 over my K. We're given a value for K, so we're going to have natural log of 2 over 4.2 times 10 to the minus 4 inverse seconds. And so when we work that out, we get a half-life time of 1650 seconds, 1,650, or 1.7 times 10 to the third, 1,700. Questions on that one at all? Okay. 27. Yes. So the log contains 60% of the carbon-14 present in a living tree. How long has the log been dead? The half-life of carbon-14 is 5730 years. The one thing it doesn't say in here, we didn't really talk about yet because we haven't talked about nuclear decay, is that nuclear decay is a first-order reaction. So anytime you see nuclear decay, it's first order. And that's the only type of half-life stuff we went over in class. That's all I would give you on this. So for 27, the key here is it says a log contains 60% of the carbon-14 present in a living tree. So that gives me my ratio of carbon at time t over carbon at time 0. The living tree is carbon at time 0 because the carbon-14 is continuously replaced as the tree gets rid of and ingests carbon. But once it dies, that ingestion process stops, and any carbon-14 left in there decays and never gets replaced. So that's why we can tell when something dies. So the formula that we want to use here is natural log of concentration of just A at time t, concentration of A at time 0 is equal to negative kT. Okay. We're looking for T, but we don't know K. However, we do know the half-life. Because we know half-life, we can solve for K. So we know that T1 half is equal to natural log of 2 over K. And so K is equal to natural log of 2 over T1 half. So that's natural log of 2 over 5730 years. And so we get a pretty tiny K here of 1.21 times 10 to the minus 4 inverse years. Okay, so now we know K. We're looking for T. We don't know our concentration of our carbon at time t or our concentration of carbon at time 0, but we do know the ratio of those two things. So that's really all we need. We know that the ratio of the carbon at time t over the carbon at time 0 is going to be 0.6 because that's 60% as a decimal. Okay? So if I'd started with 100 at A0, then I'd have 60 at time t. And it doesn't matter what I put in for A0, it's just going to be 60% at time t. So that ratio is always going to be the same. Okay, so we're going to have the natural log of 0.6 is equal to negative 1.21 times 10 to the minus 4 inverse years at time t. And when you work all of this out, you get t is equal to 4223 years. They somehow got 4210 on their answer. I don't know. You can't even round that down to 4210. I would say it's 4220. But I think it's just a typo on that part. Questions on any part of that there? Recognizing that percent as that ratio is important. All right, last page. Okay, number 28. Yep. Okay, gaseous reaction occurs by two-step mechanism shown below. We want to know what is the rate law for this reaction, including only reactants and products. In other words, we cannot include any reaction intermediates in the rate law, which is generally the rule anyways. So 28 here. So we can write our rate law directly from our slow step. Okay, so that would be rate equals K, and we're going to have the concentration of AX, Y2. It would have been nice if they made a little bit easier things to write here. Times concentration of AX. But you'll notice if you add the reaction together, AXY2 is neither a reactant nor a product present in that reaction. It is a reaction intermediate that is made in step 1 and then consumed in step 2. Okay, so we don't want AXY2 as part of our rate law. Okay, so this is a reaction intermediate. So we got to find a way to get rid of that. So we're going to go back to the reaction in step 1, since that's a fast one, and we can see by the double arrows that it reaches equilibrium. And because it reaches equilibrium, that means that the forward rate and the reverse rate are going to be the same, and we can write the rate laws for the forward reaction and the reverse reaction and make them equal to each other. So for the forward reaction, we can say that K1 is equal to the concentration of AX times the concentration of Y2. And so that's going to be equal to the concentration of K minus 1 times concentration of AXY2. Okay, I want to get the AXY2 by itself so I can solve for that. So I just need to divide by K minus 1. That's a times, not an equals. Okay, so that's going to give me K1 over K minus 1, concentration of AX times concentration of Y2 is equal to concentration of AXY2. I can now take this value here and plug that into the value for AXY2. So when I do that, I get rate is equal to, I'm going to have K times K1 over K minus 1, and I'm going to have concentration of AX, concentration of Y2, times the concentration of AX. We can combine some things here. All of our K's just become another K. And we have an AX and another AX, so that's going to be concentration of AX squared times the concentration of Y2. It's always a lot to keep track of, but just baby steps, a little bit at a time. Questions on that? Okay. Okay, 29. Okay, definition, equilibrium, forward rate, reverse rate are the same. Number 30 is our clicker question for today. Here it just happens to be A, today it's D. But products over reactants, they're multiplied by each other, and you use the coefficients from the balanced reaction as the X product. You've got the products over the reactants. Okay, how about 31? Yeah, so we didn't actually do 31, but it's easy enough to do once you see how it's done. So for 31, we've got a reaction there, and they give us the equilibrium concentrations. And so those are what we need to plug into our equilibrium constant expression. So we can say that our equilibrium constant is going to be equal to our products over reactants. So we've got concentration of NO2 squared over concentration of NO squared times concentration of O2. Okay, and so that's my equilibrium constant, and we've got our equilibrium concentration, so we just need to plug those in. And so our NO2 is 0.250 molar, and that gets squared. Our NO is 0.20 molar, and that gets squared. And then our O2 is 0.1 molar. That doesn't get squared, but when we work that out, we end up with 15.6, and we generally leave the units off of equilibrium values because in reality, they don't actually use concentrations. They use things called activities that we are not going to get into at this level of chemistry. So I believe no unit for equilibrium constant. All right. Well, hopefully you found that helpful. I will try to get this posted on a link on D2L on YouTube before 9:30. Good luck tomorrow, folks.